So now we're going to talk a little bit about data, in data characteristics, attributes, data dimensionality. So this module takes a very data-centric point of view on the topic of data visualization. It's sort of like if there's a pipe, if the visualization pipeline, you can imagine at the bottom putting like a person down at the bottom. Like the last stage is a person looking at the images. That's not, I didn't put that in the Viz pipeline, but really it should be in there. So this module takes a very data-centric view of data visualization as a topic. There are other books and modules that take a very different perspective. Like they start with the person and they work backwards, so to speak. Here we start with the data and then we work towards the brain. So when we're trying to come up with some imagery to depict data, we want to ask ourselves some very central questions. Like, what is the dimensionality of the data? Where does the data come from? Which visualization methods make sense? Why was the data collected in the first place? And what would somebody collected the data, or a group of people collected the data? What were they trying to learn when they did that collection? Data has a dimensionality. This is about terminology, really. It's conceptual, but it's also about terminology. So when we refer to scientific visualization, the word dimensionality refers to space and time. So we can have, for example, I haven't put it on here, 0D data. Does anybody know what 0D corresponds to in terms of space? A point, exactly. 1D, anybody besides Carlo? A line. Well done. 2D, what does 2D correspond to? A plane, that's right. 2.5D, there's a tricky one. Any ideas what 2.5D could be? That's a pseudo-dimensionality. It's not a real dimensionality. It's kind of a shorthand way of referring to surfaces in 3 dimensions. So a curved surface is not really 2D, but it's not 3D either because it has no volume, has no thickness. So we call it 2.5D. And 3D is a volume. So it has an x-axis, a y-axis, and a z-axis, a depth. 4D. Anybody know what 4D data is in the world of scientific viz?
Like X, Y, Z, and then that 4th dimension, and I don't know which real point.
There's a 4th dimension, and usually that dimension corresponds to something. Time. That's right. Who said that? You're cheating. That's correct. Time. So if I say 4D, I'm referring to 3D plus time. We have instantaneous or time-dependent data. So when we say instantaneous, that means time-independent. The data does not change over time. You can think of that, the analogy I usually use is like taking a photo. A photo is instantaneous time-independent data. It doesn't change over time. Whereas video is time-dependent. It's changing over time. So, like if I was talking about video data, I think of video data as 3D data. Right? It's 2D plus time. And in scientific visualization, you might remember me saying the data represents a physical phenomena, some phenomena that you can watch and study in nature usually is typically what it is. Like the anatomy of a body, of a person's body or an animal's body, motion, like motion, celestial motion, fluid flow motion, any artifact of nature. It's usually what we refer to as scientific visualization, and all those spatial dimensionalities apply. In information visualization, there's no inherent spatial reference. And in example, we'll see some examples of that. But if you took away the locations of the healthcare data, then you'd be left with just information visualization scenario. You take away the locations. But it's abstract data, there's no inherent spatial geometry. And in that case, we have to imagine or derive some spatial layout or some spatial attributes. So an example would be a graph, right? Graph is information visualization. We have to derive the graph ourselves, right? It doesn't correspond to the shape of a person's head or some artifact in nature. It's just a purely synthetic, derived shape, right? That's information visualization. And in that case, well, here are some examples. Data that's usually stored in database, text data, right? Spreadsheets, surveys, monetary data, call center data, images, sound, all kinds of information visualization. There, the word dimensionality is used differently. So, a data dimension in information visualization context essentially is synonymous with a data attribute. So if it's stored in a spreadsheet, every column in the spreadsheet we would call a data dimension or a data attribute. It's not the same as the word dimension used in the scientific visualization sense.
What would sound though would be for the
sound? It actually depends on which attributes of sound you're looking at. But classically, sound is reduced to 1D. Well, that's a tricky question actually. You have amplitude, so that's kind of like the simplest version of sound, just time versus amplitude. But there's also frequency. Wavelength, or frequency, same kind of equivalent. But there's another subtle kind of attribute of sound, which is direction. So that's too complicated of a question. You just leave that off. But usually information visualization techniques are applied to sound data, usually. But if you put it into space, you can treat it as a sci-viz challenge, let's say. And people have done this and do that. I should probably remove that. That example is a little bit tricky. Right, data has a lot of different characteristics, or can have a lot of different characteristics. The data that we usually think of is scalar data or numeric data. Right, there are different kinds of numbers, natural numbers, integers, rational, real numbers. Anybody know what a natural number is? Any mathematicians? Anybody here get a mathematics degree like previously?
Is there any integer of 0? So
Correct. How did you know that?
Because I remember naturally they didn't have a number for 0, it's just nothing. So
Yeah,
0
that is correct.
and later.
any number, like some people say, any number you can count with your fingers. Integers include the negative numbers. Anybody remember what a rational number is?
Fractions.
Fraction, any number that can be expressed as a fraction, that's right. Real numbers. Anybody remember real numbers?
Is it where it can be represented as a fraction, such as pi?
Yep, all the numbers in between the integers is another way of saying it, including the integers. Complex numbers.
Are those like E?
Yeah, they have those two, the real component and the imaginary component. That's not really important for this. It's just an example that there are lots of different kinds of numeric values or scalar values. It's not as trivial as we imagine it to be. Vectors and tensors, anybody know what a vector is?
It's shown, it's a value of magnitude and direction.
Exactly. It has magnitude and direction. How did you know that?
As way machine learning and big data.
Good. Good. Tensors, anybody look at tensors data? That's a fun data type. Not many people study tensor field data in the world. It's a very small.
It's like more than 2D data. It's like 3D, 4D, 5D, and so on.
Yep.
And they contains matrix, and matrix contains vectors.
That's right. It's a set. It's well. I have to be careful the way I say it, but I would like you could say it's more than one vector, but that's not perfectly true either. It's multiple orientations. So if you take a vector and you add the arrow to both sides of the vector, that's an orientation. And then you multiply that by 2 or 3, like you have 2 or 3 orientations, then you have a tensor. Anyways, we're not going to really talk about tensor. It's just an example of complicated data. But the physicists definitely study tensor fields. Not all of them, but some physicists definitely do. Then we also have non-numeric values, right? Text, letters, numbers, first, second, third. And we have these multi-attribute values like columns in a spreadsheet and so on, categories. We'll see lots of different examples of that in this module. And so we already talked about data having a dimensionality. It has a domain that is contained in, like a minimum and maximum value. It has other properties like distribution, scale, size, and resolution that we're all familiar with. And when we look at it, we have to make some decisions, right? How to present data. Is there an inherent spatial domain? Should we use the inherent spatial domain? In other words, is it like Simon's phenomena? If there is no inherent spatial domain, then we have to imagine one. Well, we don't really have to imagine one. We can use a spatial layout that's already been imagined for us by somebody else previously. But in information visualization, we have to synthesize or create some spatial layout, like a graph, for example, or a chord diagram, something like that. And then which dimensions are used for what purpose? What kind of presentation space do we have available? This is a very interesting question. So there's a lot of subtlety here. Like, where is the focus? So, in other words, data is not of equal importance. Some data is more important than other data. So we have to think about, okay, well, what is the more important stuff and what is the less important stuff? Can we just leave out the unimportant stuff? Right? And we'll see lots of examples of that. But these are all questions that you also want to think about for assignment 1, by the way. And there are some less interesting data in assignment 1. Some of it is more interesting than other bits. And you'll see that as soon as you look at it. Like as soon as you download the first CSV file. You'll have, at least for me, I had this this immediate desire to delete some of the columns that I just didn't think were that interesting. Right? So these are big questions. These are big questions. This is just some examples of data and dimensionality. The N is a set of categories, or the natural numbers. So the natural numbers to the power of 1, that means one set of natural numbers, being mapped to a set of real numbers. So in this case, this example, we have a set of categories, or a histogram. That's the N, discrete number. And every category is mapped to a height, an arbitrary height. Here we have a bunch of ellipses, and the thing that's changing is the radius of the ellipse. So the ellipse is the r to the 1. Right? So those are things you're very familiar with. Right? Histograms and circles. Here's an example of data being mapped to an arbitrary set of real numbers being mapped to 2D space. So we have time on the x-axis. Time can be any number, right? And then we have amplitude on the y-axis. So amplitude can be any number. These are three plots of time versus amplitude stacked on top of one another. And the user has selected a space and decided this is more important than the other ones, than the rest of the data. And then they have a zoomed in view of that important subset. Here's an example of two-dimensional data being mapped to a two-dimensional space. So in this case, the two-dimensional data is the x component of every vector and the y component of every vector. And the space is this plane, right? This two-dimensional plane. In this case, it's the same input data, but the mapping is to a texture rather than some ellipse. It's not the same vector field, but it's in both cases it's vector field data, 2D vector field data. I do have a confusing R3 in there. Anybody want to guess why I put that confusing R3 in there? There's a third dimension in the visual layout that I didn't mention.
The coordinates.
The what?
The coordinates.
The coordinates? No, it's not. Any other guesses? Time. I left time out. This is time independent, but that's a good guess. I think somebody just said it. I think I heard somebody say it. Color, yes. So really these should be grayscale or black and white. If I want to make this really R2 to R2, I would leave out the color, but I like color. So the third dimension, so to speak, in the visualization is color. So I put that confusing R3 in the And this is the range of colors here. This is a different range of colors on the right side. These are some more examples. Three-dimensional data being mapped to a three-dimensional space. So in this case, every vector has an x component, a y component, and a z component. So it's three-dimensional. And it's being mapped to, in this case, a 3D glyph, which has three components, plus color again. In this case, it's curves, streamlines they're called. In this case, it's surfaces in the third case. This is an information visualization example. So this is an arbitrary number of dimensions on the left side being mapped to an arbitrary number of dimensions in visual space in the visual design. So here we have an arbitrary number of dimensions in the data space, and they're being mapped to lines, vertical lines in the visualization space, so plotted along those lines. And this will make more sense later on. That takes some explanation. It's just an example. This is another kind of high or arbitrary dimensional information visualization. It's a glyph. And each part of this glyph represents something. Right? Anybody here watch rugby? I guess there are some rugby fans. This is like a rugby glyph, like representing a special event in rugby. So like this part of the glyph represents the time at which the event took place, assuming that the game started at this position. The thickness represents the duration of the event, and so on, right? The picture and the other parts and so on. So it represents a lot of dimensions. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10-dimensional glyph. Represents 10 different data variants at the same time. Any questions about that part so far? Okay, I guess it's maybe now is a good time to stop. What does everybody think? Yeah? We'll stop there. Happy Friday and have a nice weekend. Oh, I forgot to hand out something. I forgot to hand out the assessment sheets for assignment 1. So I'm gonna leave them, I'll leave them over here. This is how assignment 1 will be assessed. Yep, so 1D corresponds to a line, edge, it's one dimension. And then 2D corresponds to a plane, so an X dimension and a Y dimension. And 2.5D is the kind of term that we use to describe curved surfaces. So it's, imagine taking that plane and then folding it into the plane and folding it into some arbitrary shape.
I see, but the curve is not 3D.
Correct. It's 2.5D. They say 2.5D. Okay. That's correct. I cancel it. It's an optional lab. It's all labs. So I canceled it by accident. You may go to that lab. I wish you had asked that in front of the whole class. So I could have told you
You mean the next one?
correct. But you can go, if you want to go to the lab today, you can. They're all optional.
That is the page. So far I've downloaded two which are, but I've also downloaded
Okay.
which would that be super?
Yes, it would.
Okay, cool.
It's more about the visual designs that you choose rather than the actual tools.
Yeah.
Yes.
Okay. But so far I've downloaded some of the CSV. I managed to apparently I've been logging through uni. To
Okay,
use
the
it,
university
so,
might
yeah,
have.
they do like free student access. But yeah, so far I've downloaded the data. I put it into SQL Server Management Studio just to try and get it together.
It's complicated, isn't it?
Yeah. So far the biggest one is the GP England data, and then you've got just the addresses which you can join in, and then I think the other data is just the same as that. I need to go through it. So I'm putting it together. Addresses on.
Yeah, very complicated.
Yeah.
The thing that makes it kind of like noisy, in my opinion, is all the confidence intervals. You see like confidence intervals all over the place. Maybe I guess somebody looks at those. It would be interesting for somebody that like studies statistics or something to look at those and see the difference.
Yeah. Okay. Cool. Well. Yeah. And did I hear you say that you're not going to be at the lab today?
The labs, all labs are optional. I canceled the first lab for third year students by accident.
Okay.
Because usually the first lab is before the second lecture, and I always get into trouble because I forget to cancel it. I'm not going to make that mistake this year, and I cancel it for this year. The first lab is after the second lecture, so I didn't need to cancel it.
Yeah.
But you can go to that lab if you want to. It's up to you. They're all optional.
Okay. Cool.
Just
I
can help with your assignments. You can do those labs.
Yeah. Okay. I haven't started yet, so I'll just maybe start like first.
Good idea. Good idea.
Cool. All right.
Happy Friday.